Hi, I'm Eliza Wiseman. I'm a Linkerd maintainer at Buoyant, the creators of Linkerd, and today I'm going to be talking about multi-cluster failover with Linkerd. So this is me. I am a systems engineer at Buoyant. I'm a core maintainer of Linkerd, and I focus on the Linkerd proxy. If any of you are Linkerd fans, you may have seen me on GitHub or on Linkerd Slack. Um, and so here's what we're going to be talking about today. First, we're going to talk briefly about what is Linkerd, and then we're going to talk about how Linkerd can enable failover, and specifically multi-cluster failover. Then we'll talk about the Linkerd failover extension and how it works, and then we're going to do a quick demo, unless that doesn't work, which, as demos often are. So what is Linkerd? Linkerd is a service mesh for Kubernetes. We like to think of Linkerd as the lightest weight, most efficient, and simplest service mesh for Kubernetes. And what a service mesh is it's an infrastructure layer where proxies are injected into every application container, and network traffic is routed through these proxies. And the proxies are typically application layer protocol aware, so they speak things like HTTP or gRPC as well as proxying raw TCP streams. And then the proxies are coupled with a control plane that configures the proxies, rolls out config changes, and collects metrics and other data. And the sort of three pillars that we like to think of for what the service mesh provides are observability. So these proxies are positioned to collect a uniform set of metrics from all network traffic in the application. Security, as was, I think, discussed by in Jake's talk a little bit, these proxies can automatically do things like encrypt messages in flight on the network. And then finally, reliability. So we can add things like retries, timeouts, and so on at the network layer instead of having to implement them in the application. And so the failover extension we're going to be talking about today is part of this pillar of reliability. It ensures that if something goes down, that everything still works, that uptime is maintained and requests are still handled, as it says in the slide. So the Linkerd architecture, I think I sort of mentioned this. Here we have the Kubernetes cluster in blue with the little hand-drawn Kubernetes logo on it. And then we have some services here, and these are just like different pods that might be in your cluster with the purple border. And so we've got like an A service, a B service, a C service, and those are like different pods, and they're all communicating with each other over the network. And then we have these Linkerd sidecar proxies that have been injected into each of these pods. That's the little Linkerd logo here. And then we can see that like the network communication between these different pods is redirected so that all of the traffic flows through the Linkerd proxies. Then over here we have the Linkerd control plane, and that's just sort of a set of Kubernetes controllers that talk to these different proxies and send them configuration and routing, and then collect metrics from the proxies, collect other data. So that's sort of how Linkerd works. Now we're going to talk briefly about failover. What is failover, and like why is Linkerd positioned to enable us to do failover, and how can Linkerd help? So what's failover? Failover is sort of one form of circuit breaking. We've been doing failover for basically forever. It's like one of your sort of most traditional forms of like reliability engineering is that you have like some thing that is the primary service of whatever service. In this case, in Kubernetes, we're looking at kube services, which consist of a set of endpoint resources. But in general, you have something that is providing some service, and then you have some additional replicas of that thing that's providing the same service. And if the primary one goes down, then you just switch from using the primary to the secondary. That's like the most generic explanation of failover. In this case, in Kubernetes, what we're doing is we're watching this primary service, which in this example is A, and D is a client of that service. And we're watching that service, and we're looking at how many Kubernetes endpoint resources exist for it. And if everything's working normally, there's going to be a bunch of endpoints in that service. But if they all go away for some reason, then we might fail over to B or C here. Um, and so why do we use Linkerd for this? Well, Linkerd proxies are well positioned to make routing decisions, right? We've put one of these proxies in all of the pods in your cluster. And so we can very easily have them, they're sort of transparently intercepting and forwarding traffic between the different pods in the cluster. And so we can sort of very easily and transparently configure them to perform this failover. And the application containers, right, the different containers that maybe you've deployed into these pods or that are some other system that you've installed in your cluster, they don't have to know about this failover configuration. It's happening as a sort of service provided by the network layer, rather than something that every application container has to implement on its own. And so that means that rather than writing a bunch of failover code in every microservice that you might write, instead we can just configure failover behavior at the cluster level in the Linkerd control plane, and the Linkerd proxies will just automatically follow that policy. And this is sort of, in many ways, what the great promise of the service mesh concept is, that all of these things can happen as a service of the network layer. It's just provided by, if you have a network connection, then you get all of these things like these reliability features, observability features, and so on for free. And they don't have to be re-implemented in every microservice. And then, so we have, in Linkerd, we have the traffic split resource, which is provided by SMI, the service mesh interface. And Linkerd can watch these traffic splits and use them to do traffic shaping, to route traffic between different replicas. And this is something that Linkerd implements as part of its implementation of the SMI spec. And so we can use those traffic splits to do failover with Linkerd proxies. So the way that this is implemented is Linkerd failover extension. And sort of the nice thing about this is that this is not even part of the sort of minimal Linkerd deployment. This is an extension that you can choose to add if you want to use the failover functionality, but it's not mandatory. And what it is we have a new Linkerd controller, which is the failover controller. And that's sort of part of the Linkerd control plane, that when you install this extension, we add this controller. And interestingly, in Linkerd, we use both Rust and Go. The Rust programming language is used in the proxy because we want these proxies to be really high performance and efficient. We use Go for most of the control plane because the control plane is basically just a bunch of Kubernetes controllers, and they have to talk to Kubernetes, and it's very easy to write them in Go and use like client Go for that. But the failover extension, its controller was the first Linkerd controller that we implemented in Rust. We like using Rust, and the Kubernetes ecosystem in Rust has finally reached a point where it's maybe mature enough to write control plane components. And this is sort of a nice thing about the model of the control plane consisting of all of these sort of small independent microservices, is that, it's also a microservice application, right? So we can just write this controller in Rust, and it's actually quite simple. And what it does is it watches for traffic split resources from the SMI spec, and it's looking for a label failover.linkerd.io/controlled by, and that's saying, hey, this traffic split is a failover traffic split, rather than another traffic split that you might be using for other forms of traffic shaping. And then when this failover controller sees traffic splits that match this label, it configures the proxies that consist of, or that are like in that traffic split, the proxies that would execute that policy, with the details of what to do if one of the primary service in that traffic split becomes unavailable. And here's just sort of an example of the traffic split configuration. So we have a little bit of metadata here, and we're saying, okay, we add this label that says this is a Linkerd failover traffic split, and it's not part of some other thing that might use traffic splits. And then we say, here's this annotation that says this is which service is the primary. And then we have a spec that just lists the backends. And as you can see in this traffic split, we have weighted the primary service with a weight of 1, and all of the other services with a weight of 0. And what that means is, we're not going to send any traffic to any of the secondary services by default. By default, we're talking to only this primary service. And then when the failover controller detects that the primary service has gone down and has no endpoints in it, then this traffic split will be updated so that it's reweighted so the traffic goes to the other services in the the failover services. And so this is very nice because it means this is not really something that's implemented in the proxies specifically for failover. Instead, the proxies just know about the traffic split resource, and the controller knows about the traffic split resource, and it watches the traffic splits, and it watches the services and the deployments in that traffic split, and then it updates the traffic split. And then the rest of the Linkerd control plane watches the traffic split and tells the proxy what to do based on it. So the sort of nice thing about this is that the failover controller is communicating with the proxies and the rest of the Linkerd control plane and the Kubernetes controllers just by watching Kubernetes resources. It doesn't actually know how to talk to the proxies at all. It just updates this resource. So I'm going to do a quick demo of this. And the thing that I'm going to demo is also, oh, okay, thank you for, is the font size good? Can everyone see that okay? All right, so what I'm going to do is I have I've got two clusters running here. And in both of these clusters, wow, I can't type. I have deployed Emoji Voto, which is just sort of one of our demo applications that we use for demoing Linkerd for various purposes. And this is sort of a pretty simple web app. And the way that it works is we have sort of this app where you can vote on different emojis, and like you click on the emoji, you vote for it, and then it like tracks like the ranking of the different emoji that people have voted for. And this app consists of a couple of microservices. It has an emoji service here, right? And the emoji service actually lists all of the emoji. And then there's a voting service. And the voting service actually like handles votes and tracks like which emojis get more votes. And then it talks to the emoji service to get the list of emoji. And then we have like a web service that actually serves the front end. And that's sort of the like entry point to the application, and it gives you this like cute little web page where you see all of the emoji and you get to click on them and vote for them. And it's talking to these backend services. And then finally here we have a little load generator, VoteBot, and VoteBot is just voting for stuff. And what we actually can do is I'm going to just open the Linkerd dashboard, which is provided to us by the Linkerd Viz extension. And it might take a moment to open because it's opening me a web browser. Come on. There we go. So where's my dashboard? There we go. Okay, so I'm going to add another window. Or can I even... So I'm sharing this Firefox window. Can everyone see that? Okay, there we go. So I have this Firefox window, and here we just see this is the Linkerd dashboard. And if we look at this emoji voto namespace, this is the topology here that I was describing. We have this web service. VoteBot is talking to the web service, and then it's talking to the emoji and voting services. You can see we have some deployments here. And Linkerd is giving us all of these metrics and stuff. We can see like requests per second, success rate, and it's just sort of one of the features that Linkerd always provides. And then we have some traffic splits that are already created in the cluster. This one is a traffic split between the emoji service and the emoji service east, which, oh, okay, so that was the other thing that I actually forgot to mention, is that I actually have two clusters here. I have a west cluster and an east cluster. And what we're going to do in this demo is we're going to failover using both the Linkerd failover controller, as I mentioned, and also Linkerd's multi-cluster gateways. So what we've done here is we've actually gone ahead and we have configured Linkerd multicluster. I'll show that in a minute. And then we have also already installed the Linkerd Failover controller, which if we look at the Linkerd control plane, or I think it's installed in its own namespace. Yeah, so we have the Linkerd gateway, which is this is just showing that we have Linkerd multi-cluster installed, but right now we're not actually doing any cross-cluster communication. And then I'm going to switch back to, I'm going to stop sharing this. Give me a sec here. And I'm going to switch back to my terminal. Should have shared the whole screen. Okay, so I'm going to switch back to my terminal. So I'm currently pointed at the, hang on. Currently I'm pointed at this east cluster. And I have some pods here. And I have the Linkerd control plane installed. And I still can't type. Okay, so I have Linkerd control plane, I have Emoji photo, and then I'm going to do the same thing, except I'm going to look at the west cluster, right? And so the west cluster also has the Linkerd control plane, and you can see these are different pods and they're in different clusters. And then going to look at the Emoji photo namespace. So that's all still there. Sorry, give me a second here. And then I'm going to run Linkerd multi-cluster check. And that's just going to show us that the Linkerd multi-cluster extension is installed and configured. So we see that all of the resources exist and that we've created a mirror service. We have a link. That means that Linkerd is now mirroring one service in the other. And so what we're going to do is if I run Linkerd viz stat traffic split -n emoji context west. So this is going to show me the traffic split that currently exists in the west cluster. And so as we see, we have this traffic split, and it's currently configured to send traffic from emoji service to emoji service in that cluster and to emoji service in the east cluster. And I actually think this looks like it already failed over while I was running through the demo previously, which is not supposed to be what's happening. So that's actually kind of oh I see. So no, this is not the failover traffic split. This is just a regular traffic split. My bad. And so what we're gonna do if we run so if I edit this traffic split, and I should probably have shared my whole screen because now I have a Visual Studio Code window. How do I stop, share? I clicked on the wrong thing. Sorry, this is a little bit of a mess. So, okay, I have this traffic split, and this is just a standard traffic split. As you can see, this one does not have the annotation that shows that it's managed by Linkerd Failover. And right now, it has assigned all of the traffic to go to Emoji Service East, but we're just going to change that. We're going to change it so that instead we send all of the traffic to Emoji Service West, which is the one that is in the cluster I'm currently editing. So if I close that, and I go back to my Alacrity, and now we run stat traffic split again. This might take a minute to propagate. Okay, so now we have shifted all of the traffic back to the version in this cluster. And that's just sort of a demo of how we can use traffic splits to do traffic shaping. That wasn't actually the failover traffic split, that was just sort of an example. So what we're going to do now is I'm going to show how Linkerd Failover will actually automatically do essentially the edit that we just did to shift traffic from one cluster to another. So to do that, I'm going to start by So I'm going to just delete this traffic split that was used just to demonstrate traffic splits. Okay, so I've deleted that. And then what I'm going to do is I'm going to apply a new traffic split that's actually going to be one that is managed by Linkerd Failover. So I'm just going to show that file first. So here's the YAML for this, and this is going to be in the West cluster, and as we see, here we have this annotation that's telling Linkerd Failover, okay, Emoji service is the primary service, and then we have this label that tells the failover controller that it can manage this, and then by default we have assigned all of the traffic to Emoji service in the West cluster. But we've also added these other services as backends to this traffic split. And then there's also a config that's going to deploy this Emoji Service 2 in this cluster, which is like a backup service in the West cluster. So what I'm going to do is apply this YAML. Okay, and I've created this traffic split, and that actually doesn't alter anything. Oh wait, did I applied this in the wrong cluster? My default is the East cluster. My bad. So I'm going to apply this in the West cluster. Oh. I'm doing a great job at this demo, sorry about that. So I'm going to apply this in the West cluster. And now it's created. And I'm also going to apply this YAML for a second emoji deployment. And we can look at that too. So we have the second deployment, and this is just deploying this service again. We don't have to go through the whole thing. I'm going to apply that config as well. And this doesn't actually change anything. Because this is just creating this traffic split, and right now all of the traffic is still set up to go exactly where it's been going. But what I can do is I'm going to make a quick tmux split. You know, I would rather have a vertical split. Okay. What is the name of the Linkerd failover pod? Okay, there we go. Supposed to be get pods. Okay, and so we're just going to watch what this failover controller actually has to say. Oh, I need the... Okay, so here are the logs from the failover controller. And as we can see, right now it hasn't really done very much. It looked at the initial traffic split, checked for whether it was necessary to update that traffic split. It did not need to update that traffic split. So right now everything is normal. However, this traffic split that we've created here is configured so that if the emoji service fails, then the traffic is going to fail over to these two failover backends. And what we're going to do now is to simulate that failure. I'm just going to scale down the emoji service in the West cluster. So scale, deploy, wow, I can't type, and emoji. So I'm going to scale the emoji service down to 0 replicas. I'm going to do that, and now we see, okay, so this traffic split controller, it noticed that now there's no endpoints in that service, and then it patched the traffic split to fail over to the other backends. So if we run okay, I meant, my bad, that's a Linkerd command. So I'm going to use the Linkerd CLI to run to get the stats on the traffic splits in the West cluster, and that's going to just take a moment. Okay, so have I not scaled down to 0 replicas yet? Huh. It looks like we're still talking to... Did I actually deploy... Yeah, I did. I deployed the traffic split. this stack. Hmm. Okay, so my emoji service has no replicas in it. And what we're doing here is we have failed over so that some of the traffic is going to the backup service in this cluster, and then some of it is going to the emoji service in the east cluster. And right now it looks like it's basically all going to the backup service in this cluster. But what happens if we also scale down the local backup service? So that's emoji 2 here. What if we scaled that to 0 replicas? And the failover controller hasn't given me any logs yet. Run stat ts. Um, oh, okay, so we failed over to the east service. I totally missed that. Sorry the demo was kind of a mess, but it did work and I just wasn't paying attention. So I'm gonna call that. I'm going to stop sharing the screen and go back to the presentation. Can I? Oh, there we go. I have to click on it. So yeah, we do have a little time left in our budget for questions, unless I'm almost out of time here because I forgot which.
No. You're good. You're so good. There are some questions as
Okay,
well.
let's do some questions. Let's get some questions.
Yeah,
Yeah,
I
and
got.
also if you, oh, sorry, go ahead, Lisa.
Well, I feel like there might be an inside joke here that I'm missing, but I love donuts as everybody else does. So, like, what's the joke about the donut?
Okay, so the joke about the donut is that another thing that we use this demo app to demo is yeah. Okay, so Guy has seen Emoji Photo before, and what we do is we use this application to sort of demo Linkerd metrics and how you can use Linkerd metrics that we're automatically collecting for you to sort of diagnose errors and get summaries of what's happening, including using Linkerd service profiles. We can get metrics per route. So we have a demo where we show, okay, there are like all of these different votes that are happening, and most of them have like a normal success rate. All of the vote requests are succeeding, and the donut emoji fails. And it always returns an error. And so then we can go into the Linkerd dashboard and show, oh, like the donut services, or the donut, like vote slash vote slash donut is like always failing. And we can see
Oh,
that in the dashboard.
such
And
a
we can see how it
tease.
affects like the overall success rate, and so on, which is why you're not supposed to vote for the donut.
Such a tease. Okay, all right, no problem. I'm gluten free anyway. I really should not be eating donuts.
Well, then probably shouldn't vote for it. What if you got a gluten-free donut though?
I know.
It's an emoji. You can't tell.
If someone could make one, that's why I love emojis. None of them make me fat. Okay, so we do have
There's a
some.
little bit of Linkerd trivia, Linkerd emoji photo trivia,
Yeah.
specifically, which is that there used to be another emoji that you
Yeah,
could
there
not
did
get
used to
voted
be. It
for.
used to be a different emoji.
So if
But
anyone knows what it is, you could guess it in the chat.
yeah, so
I
that
have some here.
emoji was changed for uh, professionalism reasons.
I was gonna guess the little pile of
It was, yeah, that's
It
right.
Crap.
was
You
that.
nailed it.
Wow. Yeah, first
Yeah, it used to
try.
be the poop emoji, but now it's the donut emoji.
It's the first thing everyone's gonna guess because
Yeah.
we know the humor of engineer humor. Yeah, that is also one of my favorite emojis.
I
So
mean, yeah. So do we have any other questions from the audience?
we actually do. Risha, you had a couple of
Yes.
them.
Yep.
Oh, Risha has some questions. Let's hear Risha's questions.
I do, which is, and you, I mean, you touched on this a little in the talk as well, but just to emphasize, is multi-cluster required for doing
No, it's
this
not.
failover?
Right. So we actually we showed how we had a traffic split between two replicas in the same cluster, and the failover controller just watches traffic splits. It actually is completely independent of Linkerd multicluster. Um, so Linkerd multicluster, the way it sort of works is you create these mirrored services that represent a service in a remote cluster, and the multi-cluster gateway sort of routes traffic between those sort of fake services in the local cluster and the like real service in the remote cluster. So the mirror just sort of appears to services in the local to everyone in the local cluster. The mirrored service sort of appears exactly the same as any other Kubernetes service, but it's actually just sort of routing traffic through the Linkerd gateway to the other cluster. So if you have a multi-cluster mirror service, you can just put it in the failover traffic split or any other traffic split, right? So um, you could do traffic shifting through other mechanisms or for reasons other than failover, like say we want to take this cluster offline for maintenance and we want to like progressively drain traffic from this cluster to that cluster. You could manually edit a traffic split, or if you wanted to do something like one cluster has like you want to do like blue-green deploys across clusters, you could have a controller that's like editing a traffic split to shift traffic between two clusters. But also you can use traffic split to shift traffic between two services in the same cluster. And the failover controller can also do that. All it cares about is traffic splits, and traffic splits just have services in them. So it doesn't actually care at all about multi-cluster. And these are sort of two totally independent Linkerd controllers. The proxies don't know about them either, really. Like the proxy just thinks of all of these things as Kubernetes services that it knows how to talk to, and the control plane is telling it who to talk to. And the Linkerd control plane happens to be like aware of these different Kubernetes resources, and actually both the multi-cluster and failover are Linkerd extensions. So this is sort of modular. They're not really part of the like core Linkerd distribution that's like necessary to run Linkerd. These are all things that you can choose to add if you need them.
It's pretty cool how they all fit together, though.
Yeah, exactly. It's sort of we have a bunch of modular pieces, and they all communicate primarily using Kubernetes resources, right? So it's very Kubernetes centric, and it's just there are some CRDs such as traffic split which is part of the SMI spec, and everything is just really communicating in the sort of Kubernetes way by looking at these different resources and running controllers that modify them. Some other questions. Aaron Friel, I see in chat, asked why write a Kubernetes controller in Rust instead of Go. Well, one reason, honestly, because we can. The Linkerd proxies are written in Rust, and they're written in Rust because the proxies performance is really important because we want to actually, inject these proxies into every container in your cluster, and we want to actually route all of the traffic in your cluster through these proxies, right? So if all of the network traffic is going through the proxies, you really care about what is the latency that these proxies are adding. Some amount of latency is inevitable for adding another network hop, right? But you really want to minimize the latency impact, and especially you want to minimize the impact on tail latencies. And tail latencies are often a problem in garbage collected languages like Go, Java, most programming languages that you might want to write like your web applications in. And it makes a lot of sense to write like the actual backend applications in these languages because they're easy to use, they're very popular. But for the proxy specifically, we really need to minimize that latency impact. We also really need to use as little memory as possible, um, because we, again, want to put one of these sidecar containers next to every container in the cluster. So there's kind of a cost that scales with the size of the cluster. So we need them to all be as resource efficient as possible. And then finally, we really want them to be secure, because we're essentially taking this proxy and we're saying all of the traffic is going through it. And if it gets compromised in some way, if there's exploits against it, then that proxy is, and especially if the proxy is also responsible for things like managing MTLS, right? Then it's getting plain text traffic and sending it and somewhere else encrypted, and then the proxy on the other end is decrypting that connection. Then it's very, very important that this proxy doesn't have like security vulnerabilities in it. And so, there are a lot of proxy projects that are written in languages like C or C++ for performance reasons. Like Nginx and Envoy are both proxies, and Envoy is written in C++, Nginx is written in C. And those are great choices for performance reasons, because those are also not garbage collected languages. But we were very concerned about security in these proxies, and C is sort of notorious for its various like memory safety related vulnerabilities that is very easy to introduce when programming in C. And we also just wanted to use like a much more like modern language that's a more pleasant experience to code in. So we chose Rust for the proxies, and in some ways it was sort of the only option. For the control plane, writing Kubernetes controllers in Go is sort of a very natural choice, right? Because the Kubernetes ecosystem is very, like Go is very, very popular in Kubernetes ecosystem. It has some of the best libraries for like client Go, right? Is sort of the standard Kubernetes client library. So most of the controllers are written in Go, and that's mostly been quite good. But we wanted to, honestly, we wrote the traffic split controller in Rust because we wanted to try it. Because the Rust ecosystem for writing Kubernetes controllers, the sort of Kubernetes client libraries and stuff, have really come pretty far in the last like year and a half. There's like a lot of progress there. And we wanted to see what it would be like to write a Kubernetes controller in Go or in Rust, and this one is kind of simple and self-contained, so it was a fun project to try it out. We've also been introducing Rust into the Linkerd control plane with the policy controller. And I think the main reason for that is just that a lot of people on the team at Buoyant like writing Rust, and we also like that it's very easy to write high performance and fault tolerant programs. Some of the like performance benefits matter a lot less for controllers that aren't like handling very high throughput traffic. But it's just a familiar language that we enjoy using, so that's really the main motivation. Go works great for Kubernetes controllers. In some ways, the Rust experience is not quite as good because the client libraries are not quite as mature, but they do exist now, and they work pretty good. Do we have time for like another question, or are we about done here?
I think we can squeeze in this other one from the audience.
Yeah. Okay, so how does a traffic split vary from a Kubernetes ingress? A traffic split is really about shaping traffic within a cluster. It's not like an ingress resource is also saying like here is how traffic is coming in from the outside world, and it's defining some rules based on how that traffic is routed. That's not really what a traffic split is. A traffic split is about it's not actually like routing based on like a header or a path. Instead, it's sort of probabilistic traffic shaping, right? So in the demo, we saw that there were like different backends in the traffic split, and they had different weights. And in the demo, most of the time the weights were like 1 or 0, but they can also be less than that, right? So it can be like probabilistic, and what the traffic split resource is really doing is it isn't. So I guess maybe a very technical explanation is that like one way to think of it is that we have these proxies, and the proxies are both routers and load balancers, right? So a router is like deciding based on this request or based on this connection, like what service do I send it to, right? And that service might have like a number of different endpoints in it, and then those endpoints are kind of identical, or at least they serve the same service. And so then within that, we're going to like load balance across those different endpoints. And what the traffic split resource does is not really a form of routing, it's more of a form of load balancing. Um, you sort of expect that everything in the traffic split is serving the same service. They might be different versions, they might be in different clusters, but they're providing like the same APIs, right? And you are sending the same requests across that traffic split, and you're just distributing it based on like some percentage goes here, some percentage goes there. But they should all be like serving that traffic in the same way. And so that's intended to be used for things like blue-green deploys, right? Where if you have like some changed version of a backend service, you might want to deploy like some replicas of that, and you might want to have a traffic split that sends like you start with sending only 5% to the new version, and then if it works, you keep increasing the amount of traffic that you send there and progressively like roll over to that new version. Or similarly, the failover, you don't fail over like between two things that are different, you fail over between two things that are the same. Um, and the ingress resources routing rules are much more about, you know, if this is like a request that has like slash users in it, it goes to the user service, and if it has like slash profiles in it, it goes to the profile service or whatever. Whereas the traffic split, you would create a traffic split for the user service, for example. Um, and are we maybe
Yes,
getting ready for the next talk? Okay.
we are.
So
Thank
the
you
one
very
thing
much.
I am contractually obligated to put on the screen is that if you're a Linkerd fan and you want to work with us, we are hiring. We are hiring for a number of roles, including dev advocates and also Linkerd developers. So if you want to work on proxy stuff with me, we're actually hiring someone to write Rust. And if that's something that you're interested in, here's a URL you can check out, or see me after class. Here's my email and stuff.